is Melinda Galfi. So Melinda's currently a lecturer at the British University in Amsterdam. Just to give talk a bit about her career in a glance. So before pursuing a scientific career, so Melinda studied economics and worked in the field for several years. But her career scientifically, her scientific career really started in Hamburg, Germany, where she completed both her undergrad and graduate studies in meteorology. She completed a PhD there, where she focused on studying extreme events in atmospheric and climate models, particularly exploring the use of extreme value theory and large deviation theory to improve the understanding of this phenomenon. As a consequence of her PhD, she won the 2019 Donald L. Turcotte Award from the Nonlinear Geophysics section at the AGU, which is the American Geophysical Union. And following her PhD, she took postdoctoral appointments at the Meteorological Institute at the University of Hamburg, then Uppsala University in Sweden. And as I said, she's currently an assistant professor at the Institute for Environmental Studies at the Free University of Amsterdam. So we will see a bit of her research interests in this talk, which are mostly on understanding extreme events as components of climate system that produce them. Before handing over to her, I want to briefly highlight a bit of her citizenship work on top of her science work. So she's been for the past few years the lead organizer of a very large session at the European Geoscience annual meeting, which brings 18,000 people together. The meeting, not the session, but it's one of the most popular sessions on mathematics of planet Earth. So big contribution, I would say, to our community. And on top of that, during the pandemic, she was one of the leads of a big seminar series that on mathematics of planet Earth that brought together people from all over the world to watch world-class talks, and that led to actually a special issue in the Nonlinear Geophysical Processes journal that's fully available for everyone who wants to see. So it's a big pleasure to have you here, coming all the way from Amsterdam. Thank you for accepting. The floor is yours.
Thank you very much. At the beginning already. Yes, thank you very much, Francisco, for this very nice and very long introduction. It was much longer than what I sent you. Yes, but nice. So it's a pleasure to be here. Yes, as Francisco said, my name is Melinda Galfi. I work at the moment at the Free University of Amsterdam at the Institute for Environmental Studies. And I am one of these climate scientists / atmospheric physicists who tries to understand mathematical theories and to see how we can apply them to understand better the climate system and extreme events. And that is mainly the fault of Valerio Lucarini, with whom I did my PhD. And he kind of attracted me in this world of extreme value statistics and dynamical systems and statistical mechanics. So he's responsible for this evolution of my career. So the work I will show here is done with Valerio and with others as well, like Tamás Bodai, Jeroen Wouters, Gabriele Messori, and Jacopo Riboldi. But yeah, so let's start then. So what are climate extremes and why are they important? And the definition of climate extremes is actually quite straightforward. So we have a weather and climate variable, and we look at its probability density function. And then the climate extremes are in the tails of this PDF. And actually, it's also quite easy to motivate why we want to study them. because of course they are interesting from a scientific point of view because they are something anomalous, something unusual, but then they have a definite impact. So weather and climate extremes lead to financial losses, they can affect human health, lead to mortality, infrastructure damages, they damage ecosystems as well. So it is clear the use of the research work is quite clear. And then there are certain specific properties of climate extremes that lead to impact. So one of them is a very obvious one is their intensity. So for example, if we have a high wind speed during a storm, that might damage a house. So it's a very straightforward direct impact. But then sometimes the impact comes from the intensity, but also from the duration of the event. So for example, in case of heat waves are long-lasting or persistent extreme events. And what you see here is the number of excess deaths in France during the 2003 European heat waves, one of the largest heat waves of the last 30 years in Europe. And what you see is that in this period, when the maximum temperature values are very high and they are not changing, so during the heat wave, you see that the excess mortality is increasing dramatically. And now this impact comes definitely not just from the intensity, but from the duration as well. Then we have a certain connection between temporal scales and spatial scales in the climate system. And usually persistent extreme events such as heat waves or cold spells are large events as well. So here you can see temperatures during also a very recent and very extreme cold spell over the US. And so these purple values show you the very cold temperatures. And you see that basically this event, this cold spell, affects a large part of the continent. And then nowadays, a quite popular topic in climate sciences is that you can have simultaneous heat waves affecting different regions of the world, and they don't happen at the same time by chance. They are related to certain very large-scale atmospheric anomalies. So anomalous Rossby waves, which then also have a persistent pattern, and they can lead to these persistent extreme events spread all over the hemisphere. Now you imagine if this happens during the summer, during the growing season, and if you have heat waves and cold spells affecting major breadbasket regions, then you have a problem, or you can have a problem in terms of food security. And then we have our climate extremes have also the tendency to trigger other extremes. So we can have like a chain of extreme events developing. Heat waves can lead to or can intensify drought. Also the other way around, drought can intensify the heat waves, and then they both can create wildfires, which then leads to air pollution. So we have this chain of events in time, and we can have them basically also in space on very large scales. Now, how to study extreme events? And there are different approaches, of course. So we can do case studies if we want to understand the physics of certain events evolving, and if we want to understand why are they so anomalous, then we can do more an atmospheric physics approach and look at case studies. We can use, of course, statistical approaches and find common properties among all these events, among several extreme events. Or we can use dynamical systems, statistical physics approaches, and study the properties of the phase space and of the attractor. And this approach is also quite interesting because we study the extremes as part of the system producing the extremes. So I do like this approach, and I think it provides a quite deep level of understanding. Okay, so let's talk a bit about the climate system. Let's talk a bit about the system which produces these extreme events. So the climate system is a complex system with several components which are complex as well, and they are all interacting with each other. So we have the atmosphere, the air, where the weather is going on. We have the water, the hydrosphere, all these movements in the oceans and thermodynamics. We have the cryosphere, the ice sheets and permafrost, and we have the lithosphere, the Earth's rocky layer. And now if we consider only one of these components, so if we consider only the atmosphere, we are already struck by the complexity of this system. So the atmosphere is a nonlinear, chaotic, high-dimensional and complex systems. And here you can just see like a set of simplified atmospheric equations. And so we have this set of partial differential equations, and which describe the air movements at the mid-latitudes on larger scales. And so if we cannot solve these equations, right? So they are like they are a version of the Navier-Stokes equations. There is no analytical solution, but we can solve them numerically. So we can create models which then simulate these atmospheric Now, the problem is that when we transform them into models, then we reduce this infinite dimensional system into a finite dimensional system. And so there is already an error in the system. And then because of chaos, we have the problem that this error can increase exponentially. So this is why when we do weather predictions, we start, so weather prediction is an initial condition problem, right? So we start from a certain initial condition, and what we do is we use several states which are slightly perturbed to see how the error and also basically how chaos evolves. So you can see here the temperature evolution for London starting from today. This is not the surface temperature, is at the higher level. And then all these different lines, the different colors show you the different runs. So the ones which are perturbed by at the beginning. So there is a small perturbation at the beginning, and what you see is that until a certain point, which is almost 10 days from now, we can say something about the weather. So we see that for a few days now, we have larger than normal temperatures, and then we will have apparently colder than normal temperatures, but then after that, we don't know what happens. And then imagine that, okay, in case of the climate, we have all these complicated systems which are connected with each other. So the climate is really, I would say it's a monster. It's a monster of complexity. And then you can also imagine that modeling the climate system is then much more complicated, much more challenging than modeling the weather. You have to model properly all these systems, so you need those equations, and then you have to connect them properly as well. And this is also something not trivial, and it has a large effect. And then the other problem is that humans are affecting the climate system, right? So we introduce an additional complexity. We basically now we introduce a non-stationarity in the system by increasing the greenhouse gas emissions. And so when we do climate projections, the climate projection is a boundary value problem. So then the initial state doesn't matter anymore. We look at the mean evolution of the system. We look at how our attractor is changing as an effect of these changing boundary conditions. And we also don't know what we will do in the future, right? So we cannot predict the future, especially if it is related to humans. So then we use different scenarios, and we have to check the different socioeconomic evolution scenarios. And for all of them, we have to check, okay, what will happen if we behave like this, and so on. So it's a complicated thing. Weather and climate extremes are also very heterogeneous. So only in the atmosphere, we have like a very large range of different temporal and spatial scales. So we have Rossby waves of several 10,000s of kilometers size, and then we have droplets which are super small. Also related to extreme events, we have many different scales. They are happening on many different scales. So wind gusts, for example, they are quite small, so they can be like a few meters or tens of meters large. Tornadoes are then already stronger, like 100 meters larger. And then the largest are the extreme events which are related to the large-scale circulation and to its anomalies, like heat waves and maybe persistent precipitation as well. And then we have these processes which are a bit between, so they are not super big, they are also not super small. So for the smaller events, which also tend to happen suddenly, then the impact comes mainly from intensity. And in case of these larger events, impact comes from both intensity and duration. And then we mainly use two mathematical theories to study these two different cases. So we use extreme value theory when we mainly care about the intensity, and we use large deviation theory when we care about the intensity and the duration of the events. Yes. So in case of extreme value theory, let's say that we have some daily temperature variables, just an example, and then we look at the tails of these distributions, right? And we look at the distribution of the tails. Now, in case of large deviation theory, we look at probabilities of sample averages. So we basically transform, or like we don't look at daily temperature anymore, we look at monthly average temperature. And then in the case of this new PDF, you would find values which then represent heat waves or cold spares. Persistent events we think that they are large deviation theory can represent them better with respect to extreme value theory. So as we heard before, also there is no general solution. So there is no general key how to study all extreme events. There is no theory explaining all of them. And we have to find adequate tools for our specific problems and also for our specific data sets. So in this talk, I would like to discuss then two topics. The main topic is what can we learn about extreme events and the climate system based on applications of extreme value theory and large deviation theory. And I would like to discuss the extreme value theory part, and then its extensions to dynamical systems theory and these metrics related to the dimensionality of the phase space, and then large deviation theory and typicality of extreme events, which I will explain then later. Okay, so let's start with the first one. And probably already many of you know this. This is the basic extreme value theory result. This is what we call block maxima approach. And many of you probably know it as the Fisher-Tippett-Gnedenko theorem. But so here I'm just showing you what is it about. So we have some independent identically distributed random variables. And we we define blocks of equal length, and we look at the maxima of these blocks. And now the theory says that if the block size is large enough, then the probability of block maxima will converge to the generalized extreme value distribution, which is basically described by this equation. So this equation has three parameters, and the most important of them is the shape parameter. And actually, the equation looks different when the shape parameter is 0. But anyways, so this is actually a family of distributions. We have three different distributions with three different tail behaviors, and the shape parameter tells us to which one of the distributions our distribution of extremes belong. So we have the case when the shape parameter is zero, and in this case, the extremes have an upper limit. So we know that larger extremes, that these upper limits cannot occur. So this is basically what we would like to have in reality, right? Because then we could control extreme events. Then when the shape parameter is 0, this is the one shown by the black line. So extreme events are not limited. They can be also infinitely large. but their probability decays very fast, so it decays exponentially. So large extremes are basically have a very, very small probability. And then when the shape parameter is positive, so the red line here, then you have the case that the extreme events are not limited and their probability decay is also rather slow. So very large events are much more probable than in the Gumbel case. And this is where you get surprises in terms of extreme events. And this is actually the worst case, but it happens as well. So I think it's interesting when fitting these extreme value distributions to temperature or other variables, it's interesting that the temperature often has a negative shape parameter or close to zero, but still negative, which somehow tells you, okay, without climate change, the temperature values are bounded. And rainfall, for example, precipitation has often a positive shape parameter. So in case of rainfall, you can have the probability of surprises is higher. And this is also related to the recent event, the recent floodings over Central and Eastern Europe. So in that case, it was also related to rainfall, right? So it basically, this statistics, or rather abstract statistics, tells us also something about the real world. Yes, so related to rainfall, the atmosphere, of course, can contain a lot of water, and if it releases it at once, then you can have very strong events, which are very different than the weaker ones. Okay. And then this is mainly the work of Valerio, and others, as of course, extreme value theory has been extended to the field of dynamical systems theory. And here we take a rather global perspective. So we look at extremes of general physical observables, and these are located in rarely visited regions of the phase space. And then they find that the shape parameter of these observables is related to the dimension of the attractor. So there is a connection between the extreme events of my observable and the dimension of the attractor. And then they find also that this means actually that the shape parameter does not depend on the chosen observable, and that in a high dimensional system, high but finite dimensional system, the shape parameter is negative and close to zero. So now you might say, okay, but this is somehow a contradiction between what I was explaining to you before, because we do observe positive shape parameters and negative shape parameters, and they are not always close to zero. But so this is where we have the clash between the mathematical theory, which is a limit theory, right, and reality. So in reality, sometimes it takes very long, or it is very hard to observe the mathematical limit. And in that case, maybe something which is not the real value, it can represent our extreme events better than the real value. Yes, and then during my PhD, I did some model simulations with the atmospheric model representing mid-latitudinal dynamics, and I checked the convergence of the shape parameter. I checked whether it is indeed converging to this theoretical limit. And this model was very good because, quite good, because I could do very, very long simulations, so several hundred thousands of years. And I could check this convergence, but you see also that it is very hard. So it seems that several observable, the shape parameter of several observables converges to this theoretical limit, but it is very hard to obtain this convergence. The system has to be chaotic enough, and then your autocorrelations shouldn't be too strong. So autocorrelations makes this convergence slower. Then related to extreme value theory for dynamical systems, so there is also a local perspective, like on the attractor. it has been found, so if we look at recurrences in the phase space, we can connect them with recurrent weather patterns. So in the weather, we also observe again and again very similar patterns. So they are, of course, always a bit different because in reality, we never get the same pattern, but they are recurring. So this approach is useful to study them. And then there is a connection between statistical properties of extremes of so-called geometrical distance observables and the local dimension of the attractor. And this is a work mainly done by also by Valerio, but also by Davide Faranda. And Davide Faranda uses these dynamic system metrics to real atmospheric data to in terms of predictability and for other applications. So if you are interested about the mathematical details, they wrote also a book about it. So it's this book here. And then a bit about how we can use these metrics. So it's again Davide Faranda's paper here. So these are basically recurrent atmospheric configurations. So over the North Atlantic oscillation is very important, and it's a recurring pattern that it governs our weather. So for these different kinds of atmospheric patterns, they have computed the dimensionality and also another index which is related to the persistence of the events. And what they find is that certain configurations have a low dimensionality, and this dimensionality is related to the degrees of freedom your system has to evolve in a certain direction. So if the dimensionality is low, then your system does not have so much choices. And this means that those states are also better predictable than high dimensional states. So they find that certain atmospheric patterns have a lower dimensionality. They should be better predictable than others. A prominent example is, for example, blocking. It is well known that it is very hard to predict the onset and the decay of the blocking. The models do it wrong always. And you see also that blocking has a higher dimensionality than the other atmospheric patterns. So it kind of explains also these difficulties. And now these metrics are used also to basically to say attribution statement about climate change. So whenever an extreme event happens, there is a discussion about, is this caused by global warming? How much percent is this caused by global warming or not? And then Davide developed this method, kind of attribution method, where we can see whether global warming has led to a change in the atmospheric dynamics. By the way, one of the big questions related to global warming is how the atmospheric dynamics will change. The thermodynamical effects are quite clear, but the dynamical effects, they are still debated, and there is a lot of uncertainty about them. But this a bit helps to see, okay, is the dynamics of a certain recurrent atmospheric pattern indeed changing or not? Yes, so a bit of a summary for this part, for this extreme value theory and dynamical system part. So with extreme value theory for dynamical system, we can make a connection between statistical properties of extreme events and general dynamical properties of our system. The developed dynamical system metrics are useful to understand atmospheric circulation patterns, their predictability, persistence, and they are used also in studies related to the effect of global warming. Okay, now the other topic, the large deviation theory and the typicality of extreme events. So this large deviation law looks quite similar to the previous law I was mentioning with the extreme value theory, at least how we select, how we proceed, or maybe just because I put it like that. So we have some random variables. We divide these random variables into blocks, and now we average over these blocks. And the large deviation principle says that if this block size is large enough, then the probability of our averages decays exponentially with further increase of the block size. So this law is described by this equation here. This sign is like logarithmic equivalence. And you see that in this equation, so there is only the block size and this rate function here, this function. So, and this function is the so-called rate function because it gives you the speed of decay of probabilities. So, for example, in case of Gaussian random variables, we have this red line is the rate function, and the rate function is quadratic. The rate function is positive almost everywhere because the probabilities of averages decays everywhere exponentially, but it is zero at the mean of the distribution. So this would give a probability of 1, and this is then gives you the law of large numbers. But then large deviation theory is more than the law of large numbers or central limit theorem because it gives you also the probabilities of deviations far away from the mean.
So I don't want to, you said average and then that wasn't a 1 over n. I mean, I'm not.
Yeah, true. No, it's a mistake, yes.
Sorry.
Yes, no, you're right. But it can be formulated, of course, also for sums. But yeah, that's a mistake. Yes, and then I wanted to discuss a bit some properties of quadratic rate functions, and you will see later why I am so obsessed about quadratic rate functions. So if we have a quadratic rate function and if we look at anomalies exceeding a certain threshold, then we have the situation that these anomalies are concentrated around the threshold because then the probability of larger anomalies is exponentially smaller. So the averaged anomaly is dominated by values close to the threshold, and which would mean also that this threshold represents a typical anomaly. Now, if we take the same distance of anomalies, but we go more towards the tails, we see that the rate function distance is increasing, which means that this exponential difference between probabilities is becoming even larger. So this means that the more we approach the tails, the typicality of anomalies strengthens. So the threshold represents now even better a typical anomaly because larger events are even less probable and exponentially less probable. Okay, now also large deviation theory is a very large field of research. There are many different levels of large deviations. We apply mainly this basic large deviation technique, but we are also interested by other large deviation results which are related to the typicality of trajectories in the phase space. So, and I'm sure that many of you heard about the Friedlin-Wenzel large deviation theory, which considers dynamical systems perturbed by noise. And more recent results are large deviation results for dynamical systems with random components. And since we have randomness is part of our chaotic system in a natural way, these large deviation results are interesting for us. So here you see a similar law as we have had before, but now this relates at trajectories, and it says that the trajectories have to approach a very large value. So this z should go to infinity, and again you have a rate function. So again you have a most probable trajectory which your extreme events will follow. And the more extreme the event, the more it will follow this most probable trajectory, which is called then the instant on realization. Now, on the slides after this one, I will show you applications of this. So I will show you rate function estimates based on model results, and I will show you also what evidence or what signs we find in our applications which point towards the typicality of trajectories leading to an extreme state. And the basic idea of both approaches is the same. So the more extreme the event, the more it happens in a typical way. And we will check whether this is true or whatever. Okay, so first, a few rate function estimates in simple atmospheric model. Now, this is a bit of more complicated model than what I was showing you before, but it is still rather simple because it's just the atmosphere, right? Without the ocean, without water, and so on. And what we find in this model is that, okay, if we average, if we take a certain block size, we estimate the rate function, and then we increase the block size, and so on. After a certain block size, the rate functions will converge. And this is around 20 times the integrated autocorrelation timescales, which is about 1 month or so. And we see that the rate functions converge in time, but they also converge in, we calculated spatial averages as well. And we see also that these spatial rate functions converge as well. So they are scaled, of course, properly based on the temporal and spatial autocorrelations as well. And what we find is also like kind of universality of these temporal and spatial averages, because then these final rate functions, they agree with each other. Yes. But the point here is that we don't have orography in this model. So if we follow a latitudinal band, the dynamics is very similar. So there is nothing breaking the symmetry, basically. So this shows a symmetry between space and time. But then when you go to more realistic models with orography, you lose it. And then we went to more realistic models. And then we took one of the so-called state-of-the-art climate models. So this is one of the CMIP6 models with which the IPCC did the recent evaluations. And because we want to check we apply a limit theory and we want to check convergence, we need long and model simulations and in a stationary state. So we have 1,000 years, we took the 1,000 years pre-industrial control runs with this model, and we have estimated the rate function in different locations. And what we find here, so I ask you for now to ignore the blue lines. What we find here is that the rate function mainly converge for locations over the continents. And this convergence time is also 1 or 2 months. We also see that these rate functions are rather, they look quite nicely quadratic, which then would point to the typicality of temperature anomalies over continents. We don't find a convergence in case of rate function of oceanic regions. And I will leave it this now as it is, but keep in mind that, okay, so for oceanic regions, we don't see a convergence. So now a bit of investigation of the typical properties of atmospheric extreme events. I will mainly show analysis of heat waves. We find very similar results for cold spells as well. Okay, so here we took this model simulation and we select the temperature anomaly in one location marked by this green dot. And these are temperature averages over 1 month. And we select anomalies of around 4.5 degrees. And we average over all the anomalies we have selected. Now the colors show you simply the temperature anomalies, and the contours are related to pressure anomalies in the mid-troposphere 500 hectopascal geopotential height. So basically, when you have a heat wave, you have a high pressure center. A high pressure center induces a sinking motion in the air. So you have a clear sky condition. A lot of insulation can come down from the sun. Then there is an effect of the soil moisture. So this leads basically to a heat wave. And what you see, these positive pressure anomalies, they point towards a so-called blocking pattern. And what we see is that although we select these anomalies at one single point, we automatically obtain an anomaly pattern with a very large spatial extension, which points to strong correlations during extreme events. And we only select the anomalies as only the temperature anomalies, but we automatically get these pressure anomalies as well, which points towards strong correlations among these two physical observables. Now, if we select also larger anomalies there than 4.5 Kelvin, so we take all the events which are larger or equal than that, we see that the anomaly patterns does not change much. Doesn't really change. So this tells me, okay, the largest event does not dominate the mean of the smaller event, so which is pointing towards typicality. Now you could say, okay, but these are only averages over several events. How do the individual events look like? And here I show you only a few examples. So you see that the individual events we have selected, they are different from each other because we have a chaotic system, but they definitely have clear common properties. Then we wanted to check whether indeed the similarity between patterns becomes stronger when we select more and more extreme events. And here you can see, so the red dots show you the location of the maximum high pressure center in the individual events over which we average. And what we see is that the more extreme the event, these red dots, I mean, I think they are quite hard to see, especially the green one. But anyway, so the red dots are concentrating more over the green dots. So the typicality of the extreme event, the similarity is increasing. And then we, of course, checked also other locations. And again, now these are locations over North America. We wanted to study a different kind of heat waves. And again, you see that the red dots are concentrating around the green dot. And what you also see that in certain locations, so these are all local anomalies. We choose them at one point, but you see a very large spatial pattern, which reminds you at the wave anomaly, so at an anomaly of the Rossby wave. So apparently these very large scale anomalies are part of these typical properties as well. Now, I wanted to show you how the situation looks like over the ocean. So if you remember, I mentioned that, okay, the rate functions don't convert over the ocean. So we do the same for a location over the ocean, which is not far from the continent, but still what we see is that then these high pressure centers are distributed all over the place, and we don't see as a clear concentration of these dots as for locations over the continents. Now, what we can do with this kind of analysis, we can check whether actual extreme events which happened and which were all exceptional, whether they could be a typical event as well. Because whenever an extreme event happened, then you hear in the press, and then there are papers about how exceptional that event was. And we checked two events, like the two very large events, the 2010 Russian heat wave and the 2021 Western North American heat wave. This, by the way, led to that a whole town burned down in Canada. So we checked whether these anomaly patterns could be a member of our typical anomaly patterns based on the model simulations. And we do find that these could be also one of those typical patterns because they look very similar. And I point out that these were pre-industrial model simulations. So there is no climate change effect in them. Of course, this doesn't mean that global warming is not making these typical extreme events more frequent. It does. So they are still part of the natural variability of the climate, but if they happen more frequently than they should, of course, they still have an impact. Okay, so this is now I was focusing on spatial patterns. So how about the evolution in time? Because we would expect also if this typicality applies, we should see it also in the temporal evolution of heat waves. Now, this is a study done by researchers from France, led by Robin Noyel, and they checked heat waves over Europe And they checked also whether when we approach the extreme state, whether our events become more similar to each other. And then they indeed find that the more we approach the extreme state, the more the patterns are similar. And this effect is stronger in case of more extreme events. So more extreme events tend to become then more similar than less extreme events. Okay, other kinds of simulations, but pointing to the same thing. So sometimes when an extreme event happens, a climate scientist, what they do, they go back a few days before the event happened, then they perturb the state. And so they produce basically events which did not happen, but they might happen. So we can study unobserved event by this technique. And what we see is that, okay, so this green dashed line is the actual event, and the other lines are these perturbed events. And what we also see that they do follow this, so their evolution is similar to the evolution of the actual heat wave. And like from a physical perspective, the argument is that so the more extreme an event is, the less possibilities has your physical system with the finite amount of energy to produce that event. So then the more they get similar. Yes, so a bit away from heat waves, so another type of extreme events in winter. So we looked here at the connection between the jet stream. So I'm sure you heard about the North Atlantic jet stream, which basically governs our weather over Europe. And we checked the connection between jet stream anomalies and precipitation anomalies over the Mediterranean. So we use a certain jet index to this zonal jet index, which measures the split in the jet. So it tells us whether the jet is anomalously split or anomalously merged. So we use this index to select anomalous states of the jet. And then we look the connection with the precipitation over the Mediterranean in terms of relative frequency of precipitation extremes. And what we see, and basically this side of the plot, is that so the more we approach an anomalous jet state, in this case, the more merged the jet is, the more frequent are precipitation events over the Mediterranean. And this effect is stronger on more extreme levels. Okay, so to summarize the second part, based on large deviation theory, we can obtain probabilities of persistent temperature anomalies over continents, and we very often find quadratic rate functions. Now, I did not discuss actually probabilities. I only looked at the rate functions, but it is relatively straightforward to obtain probabilities and return periods from the rate functions. And related to the typicality of extreme events, we see that extreme events are often very similar among each other, and this refers to spatial patterns, temporal evolution, and also to the connection between certain physical processes leading to the extreme event. And we also see that the more extreme the event, the more it happens in a certain way, thus the more typical it is. And I've shown you that also several record-breaking heat waves were actually typical events. Okay, so a bit about the implications of this typicality for further research and for applications. So does this mean that more extreme events are better predictable than less extreme events? And there are already signs that often for heat waves, this is the case, but there is no theoretical reasoning behind. So maybe this offers an explanation to certain observations. Then it would be also interesting to classify extreme events based on whether they show this typicality or not. I don't expect that every climate extreme shows these typicality properties. And I think that this is mainly related to the large-scale atmospheric circulation. Now, if you look at local scales, if you have three-dimensional turbulence, if you have some stronger non-stationarities, phase transitions, then it probably doesn't apply. But it would be good to understand better extreme events if we would classify them based on these characteristics. And then, of course, how will typical extreme events change with global warming? It's an important question, but because these are also the most probable extreme events. So first, maybe we should prepare for these ones and then see about what to do with the anomalous ones. And it has also, or it should have also implications to how we train AI algorithms, because sometimes AI algorithms are used to predict extreme events or to generate new events. And probably if these typicality properties apply, then it's easier for the AI to be able to do these tasks, and also things related to transfer learning. Yeah. Okay, so the summary of the whole talk. We discussed basically what we can learn about extremes and the climate system based on extreme value theory and large deviation theory. I showed you that extreme value theory and its extensions to dynamical systems help us understand better the connection between extremes and the system producing these extreme events. And it provides also a useful tool to study atmospheric patterns and their change due to global warming. Using large deviation theory, on the other hand, we can obtain probabilities of persistent temperature anomalies over the continents. We find certain evidence for the typicality of these large-scale extreme events, and we can verify how exceptional extreme events are, whether exceptional extreme events are indeed exceptional. Thank you for your attention.
Thank you, Melinda, for this very nice talk. Do we have any questions?
Yes, please.
Thank you very much for the talk. It was very interesting. I was wondering whether it's possible to use these techniques to do something like assess the fidelity of climate simulations against actual
Yes.
world in the real world.
Yes, I think so. You can do that. In case of, if you want to compare it with observational data, you have the problem that it would be nice to do that, but you don't have basically enough data to obtain proper estimates of the rate functions. But otherwise, these differences in the rate functions could tell us a lot about how climate models differ from reality, or also how climate models differ among each other. Maybe this would be an interesting thing to see how the different rate functions differ among different models. Or also, if one would use, there are these large ensemble model simulations which give you enough data with a global warming signal. So what one could do is that one could check the change in the rate functions based on this abundance of data, basically, for different time periods, and one could see, okay, what is the effect of global warming?
Yeah, precisely working with one of these large ensembles.
Yeah.
Really nice tool.
Yeah, they are a nice tool. They are generally a nice tool, I think, for this kind of studies.
Thank you.
In your slide before this, you said teach AI about extreme events, not in a training set. So without any qualification, I thought I would like to know a bit more about that. And then I heard somebody behind me, I don't know who, mumble that's very dangerous. So I thought, so now I'm curious.
No, I haven't seen anything about without training set or with training set. It's not related to that. So the thing is that what we observe here, due to this typicality that, okay, more extreme events are similar among each other, and we also see that they are not very different from less extreme events. So first, if the extreme events are similar among each other, maybe it is easier to generate the artificial events, just a thought. But then also related to transfer learning, because sometimes people do transfer learning where they train the model on moderate events and then they try to say something over more extreme events. And if this typicality indeed applies, maybe this is one of the cases when you could do that, or there would be a justification to do that. So, but it's just, I didn't check it, it's just an idea.
What is transfer learning? I've never heard about that.
Transfer learning is, for example, when you train the AI, so there are different levels of transfer learning. So you train the AI model on a certain data, and then you fine tune it on another data. So you can train the model, for example, on a climate model, and then you can fine tune it on reanalyze this data to say something about more realistic events. Or you can train the model on moderate extremes, and then you can say something about more extreme events. You can fine tune it basically to make a statement about more extreme events. So you transfer the learning basically. Yes.
Surely you cannot train AI in any way on chaotic events.
Okay. You say that we cannot, or is it a question, or is it a statement?
Yes, it's not a question,
Yeah.
it's an observation. You cannot train AI. You can train it on a set of events, but if you have chaos in the process,
Oh, no, you can train
AI cannot predict anything that's happening in a chaotic system.
That's nonsense, it's really good at it. Press for computers, we really good at it.
No, it does work.
Yeah.
But why did you then muster dangerous?
Chaos has nothing to do with extreme events.
You know,
I'm thinking of something, tipping points and stuff like that.
that's dangerous.
That's dangerous.
Yes.
Tipping points. I'm not talking about tipping points.
No, I think, yeah, I'm fine with that.
Routine dynamics.
Yeah, I would just, so we have a few questions online.
I've got a question from Michaela Tobre. They want me to say on their behalf, around slide 26, but in fact also in other slides, do you expect the rate function to be quadratic? Indeed, do you always expect convex rate functions?
I always seen in atmospheric climate data, I've always seen, I always seen only convex rate functions. So I sometimes found rate functions which are not that perfectly quadratic in terms of they are not completely symmetric, but I always found convex rate functions. So, and often for temperature. In case of some variables related to wind speed, to the jet stream, one of the rate functions looks rather asymmetric. So wind speed related rate function is a bit asymmetric. Not super weirdly, but is not quadratic, definitely. But we find very often these quadratic rate functions.
I have another question from Nick, who we heard from earlier. Another option would be data augmentation, amplifying existing moderate events to be examples of extreme events. This could be a productive place for classical statistics to link up with AI models to help do this data augmentation well.
Sorry, the question again, please, just the end of it.
This could be a productive place for classical statistics to link up with AI models to help do this data augmentation well.
I don't know much about data augmentation, yeah. So, but it sounds a bit like the problem he was mentioning. It's a bit like related to like the same idea as behind transfer learning. So, using moderate events to go towards more extreme events, right? But yeah, I think I cannot answer the question.
Yeah. Well, I think in the interest of time, I know it's lunchtime, so I'll just end now. So let's thank Linda again.
we